Welcome to this explainer. Today, we're cracking open the examiner's playbook for the Cambridge Additional Mathematics syllabus. We're specifically looking at course 0606. Listen, if you've ever felt like you're doing all the complex algebra perfectly, flawless calculations, but you're somehow still dropping marks, you are definitely not alone. It is incredibly frustrating. Today, we're zeroing in on a surprisingly simple yet absolutely crucial skill: clearly labeling points of intersection with coordinate axes. Think of your exam strategy like being a master tailor. You need to tailor your answer to fit the question perfectly. No loose threads.
And the stakes for this specific detail? They are literally game-changing. As this quote highlights, the difference between a B and an A star often comes down to this exact requirement. Examiners aren't just looking for a final number at the bottom of a page. They want visual proof. They want to see that you understand exactly how those algebraic equations translate into actual geometric space. Leaving your axis intersections unlabeled? It's like writing a brilliant, persuasive essay but forgetting to use any punctuation. It leaves the examiner guessing, and let me tell you, examiners simply do not award A stars for guessing.
So here is our roadmap for today. We'll start with the A-star difference, then move into the theoretical foundation, break down the technical methodology, and finally look at top examiner warnings. Let's dive right in.
Section 1. The A-star difference. Now you might be wondering, why do students actually struggle with this? Well, senior examiners have identified a foundational issue. A lack of precise definitions is causing students to bleed easy points. Think about the difference between a beautifully drawn parabola with just a vague x next to it versus one that has clear, precise coordinates written out. If a command word asks you to find the coordinates or show the intersections, merely sketching the general shape just isn't going to cut it. The actual numbers must physically be on those axes.
And this perfectly illustrates what examiners are actively hunting for. They want deep, causal relationships. They want to see cross-topic connections, not just a shallow, superficial overview of raw mathematical facts. Superficial breadth is knowing the mechanics of how to factor a quadratic equation. But analytical depth, that's understanding that the roots you just calculated are the exact physical places where the curve crosses the x-axis, and then proving that understanding by writing those precise coordinates on your graph. That visual labeling is the bridge that connects your algebra directly to your geometry.
Moving on to Section 2, the theoretical foundation.
So the crucial point here is that top-performing students, the ones getting those A stars, don't just memorize formulas. They rely on systematic analysis and evidence-based reasoning, so they can adapt to completely new problems. Cambridge calls this connected conceptual understanding. Basically, when you label an intersection, you're demonstrating to the examiner that you fundamentally connect the algebraic concept of setting x or y to 0 with the graphical concept of an axis intercept. It's exactly this kind of knowledge transfer that gives you the power to tackle that weird, totally unfamiliar 10-mark question that's always waiting for you at the end of the paper.
Think of it like leveling up in a game. You have to progress through these higher-order assessment objectives. You start at the basic descriptive level, simply stating the facts or writing down an equation. Then you level up to analytical, processing the methods, manipulating the complex algebra. But to hit the top tier, you have to be evaluative. By actively labeling your coordinate axes, you prove you're operating at that highest level, showing exactly where that mathematical curve actually sits in two-dimensional space.
All right, let's get practical. Section 3, the technical methodology. This right here is your standardized sequence. Following these steps guarantees you extract data and interpret relationships perfectly every time. First, identify that intercepts are actually required by the question. Second, apply the principle of setting your variables to 0. Third, execute your algebra with crystal clear working. Fourth, verify that your numbers actually make visual sense on the graph. And fifth, this is the one everyone forgets, present it. Literally, physically write those coordinates right next to the axes on your sketch.
Going back to that fashion designer metaphor, you have to wrap your work in strict conventions, so there are absolutely no loose threads. Proper formats, clear annotation, that's what clearly labeling points of intersection is all about. Look, an unlabeled graph is just a line floating in the void. But a graph with clear, precise annotations of coordinate intersections, that is a rigorous, undeniable mathematical argument. And it's one that examiners are more than happy to award full method marks for.
Which brings us to the final piece of the puzzle. Section 4, Top Examiner Warnings.
Pay close attention to this because it's a direct alert straight from the principal examiner reports. Candidates consistently confuse terminology, which creates ambiguity. Are they asking for the coordinates formatted in brackets or just the raw x values?
Don't leave any ambiguity on the page. Your visual labeling is exactly how you clearly define the boundaries of your graph, establishing your logical reasoning for the examiner right from the jump.
Let's look at the top 3 pitfalls. If your analysis ignores these, even a perfectly calculated answer is going to lose points. Mistake number 1, forgetting proper format. Writing x equals 5 when the question requires the coordinate pair format of 5, 0 is a classic heartbreaking error. And mistake number 2, not checking presentation. In this context, that translates directly to drawing a beautiful curve, feeling great about it, and just walking away to the next question before actually labeling the intersections.
So how do we guarantee we don't make those mistakes when the clock is ticking? You need a memory hack. Create a mental trigger for yourself. Something like CLIC. Calculate, locate, intersect, check. Whatever works best for you. The goal is to make sure that trigger fires the exact moment you're asked to sketch a function. Tell yourself, the job simply isn't done until those axes are labeled.
So as you move forward and start hitting those past paper questions, I want you to ask yourself, what is your mnemonic going to be? How are you going to implement this framework today to fundamentally change your exam strategy? Are you going to be the student who leaves their brilliant algebra floating out in space? Or will you be the candidate who tailors their answer perfectly, proving your connected conceptual understanding with clear, labeled intersections? The choice and that A star is entirely in your hands.